Now, in this session, we will we'll get into our second theorem. We will find an example of a second language that is, well, actually a third, but our second language other than a suffix tm. So it'll be our second language in this chapter. The second time round of proving, supposedly using reducibility technique to show a language is undecidable. Now, before our first example, this chapter, was halt tm. And our second one is going to be e-tm. Now we've seen this sort of thing before, except we didn't have tm here, we had something else, some other kind of machine, or grammar, or whatever. But yeah, we've seen this sort of thing before. So here's the language we're talking about, and we will prove in theorem 5.2 that this language is undecidable by using the same kind of approach as we did in 5.1, previous theorem. So what is this language? Well, it's just the set of strings where each string is an encoded description of a Turing machine. Right? Such that, and there's a condition of course, that M's a Turing machine, and that the language that Turing machine accepts is empty. That's the empty, not empty string, it's the empty set. Right? In other words, there's nothing in that set, it's the empty set. And remember this terminology, this is the language that M recognizes. I think that's correct. Yeah. Right? So you can have all possible Turing machines. You apply this L to it. You find all the you get. Imagine an infinite list, a countable list of Turing machines, M, and you find the languages that that Turing machine recognizes, and if the language is empty, then put the description of that Turing machine, M, angle brackets M, put that into this language. Okay? So in other words, this language consists of descriptions of all Turing machines that recognize nothing. so the languages they recognize are empty. Okay? That's the condition. Right. Now this language is undecidable. That's the theorem statement here, theorem 5.2. Now, proof idea. In fact, we'll have 1.5 squares on the proof idea, but we ran out of board, ran out of session, so we won't be able to even start on the actual proof. And be warned, the abstraction level is getting harder. Some of you maybe will have some difficulty following this. This textbook is part of it definitely is M1 level, master level. So I would say this half and the next square are definitely master's level. Right? The abstraction level is non-trivial. All right. Now we will do much the same kind of thing as we did in the previous theorem. So again, in global terms, proof by contradiction. Right? So we'll follow the same pattern, the same kind of thing as we did in the previous theorem. So now trying to show that this language here, with this property, is undecidable. So assume this language is decidable. In other words, we're using proof by contradiction, right? So assume that it is decidable, and derive a contradiction, proof by contradiction. And what contradiction would that be? Well, if this is decidable, then ATM is decidable. That's the strategy of the proof. So the guts of the proof will be, if this is true, in other words, there'll be some Turing machine that decides this language, then you can deduce that ATM is decidable, and that's the contradiction, of course. So that's much the same as the previous one, because we know that ATM is undecidable. That's the contradiction, and hence this must be false, and hence ATM is undecidable, right? So the proof boils down to showing that if ETM is decidable, then ATM is decidable. Okay? So how to do that? Well, again, much the same way. We will assume, now given this is, if we're assuming this is true, then by definition that means there's some Turing machine that decides this language. Let that Turing machine be R. Okay, so that's a Turing machine that decides this. And just as we did in the previous theorem and the proof idea and the proof, we will construct a larger Turing machine S that calls or uses R, and we will design S in such a way that it decides this language, ATM. And we will use R to help us in this task. The task being that we'll have this larger Turing machine S that has Turing machine R as a component, and we'll have this Turing machine S decide this language. Now if we can do that, we've got our contradiction, because we know ATM is undecidable. Right. Okay. So again, be the machine S yourself, and ask yourself, how would you go about trying to decide ATM, given that you have this machine R that decides this? How could you do that? Right. So imagine, how would you work if you're this larger Turing machine S? How would you react on this input? Because this will be a member. No, it's not. It's not a member. Keep falling into that error. So for any Turing machine and any string, that ordered pair will be a member of this language if M accepts W. Right? And S is supposed to decide that. So S will accept if M accepts W, and S will reject if M does not accept W. But there's two ways M might not accept W. One is that it just rejects it, and the other one is that M loops. Right? So we've got much the same kind of problem again. Right? Now, okay, so we're looking for ideas now. So one idea is to have S run R. So R's a component, a part now of this. So let's have the larger Turing machine S, let it call on R, makes R run on the input this. Okay, and see if R says that it accepts. Now remember what R's doing, right? It's a decider of this language, a decider. all descriptions of R will accept these strings of this language if the language of this machine M is empty. Okay, so have S use R and input this to R and see what happens. So if machine R, tuning machine R, if when you input this and it accepts, R accepts, what does that mean? Well, it means that this it means that this is empty, right? Because that's the condition that it's here in this language. You know, the language of that machine is the empty set. Okay, so we know that is empty. Okay.